So thank you for the introduction. Let's make a start. So at SimScale, we work with many automotive firms, and in the automotive industry, we're seeing a need to go faster. Engineers need to move faster. And we're seeing that across the board. And this is mostly because of some of the macro trends that we've got: electrification, powertrain shifts, shorter programs, lower volumes, and new OEMs in the market. And what we're hearing from a lot of the suppliers, especially to the newer OEMs, is that timelines have shrunk significantly. So where they used to have 4 to 6 months to respond to an RFP, they now have as little as 2 weeks to respond. And as much as 80% of that technical engineering work is expected to be completed prior to actually starting the project. So this is putting a lot of load at the early stage of the project. And this is where we're seeing a need to move faster and a need to be able to front load the simulation at the start of the project. And we're seeing this theme across the industry. It's not only in the automotive industry, but we're specifically seeing it in the transportation industry, electronics, the industrial, and the medical. And we're seeing in the automotive industry that shorter RFP response time is driving things. But in the other industries, like the electronics industry, there's a need to get products to market, more products, and get them to the market faster. In the industrial area, the need to transform the portfolio while managing margins. And in the medical industry, it's all about who can get accredited and who can get to the market first. So there's a need for speed in all of these. And that's a topic that I want to touch on throughout the whole presentation. It's a theme that I'll be covering. And at SimScale, we empower engineering teams to innovate faster. So we're addressing this speed bottleneck. And we're doing that by making engineering simulation truly accessible at any scale. So we're putting high fidelity, fast tools in the hands of design engineers as well as simulation experts. So let's frame the problem that we're talking about a bit more. So we've talked about this problem where we need to have a faster rate of innovation at an early stage in the design process. Well, the simulation lead time here is a rate limiting bottleneck in engineering processes. So with the traditional design and simulation approach, the design engineer or the design function will come up with a new design, and then they'll typically hand that over through an internal system to the simulation department. Now, there's always a simulation lead time associated with when the simulation department can pick up that job. Some things are higher priority and will be done sooner. They might be done the same day or the next day. Other things may be deemed lower priority. There may be a backlog and loading on the simulation team, and they may take longer before they can be done. So there's a delay before that design engineer actually finds out the critical insights that they need to know about whether their design is good enough to pass to the next stage or whether they need to iterate some more. And when there's an iteration, there's obviously a simulation cycle time. So we have a simulation lead time until a simulation can start, and then there's a cycle time. And if it's a different department, this cycle time can obviously be quite long because the simulation person will go back to the design team and say, you need to improve in this area. We've got cavitation or we've got circulation, and that whole process will extend. So if you've got a squashed timeline and you've got to respond to an RFP in 2 to 4 weeks, you probably only have enough time to do 1 or 2 of these simulation cycles. So you're really limited if you're using a traditional approach. Now we're addressing this with our tool stack, and we're addressing it in multiple different ways. One of the ways that I want to focus on today is how we're addressing this with foundation AI models and engineering agentic AI in SimScale. So we're really looking at being able to ask a high-level question like, design me a pump that meets these pressure head requirements with this electric motor driving it. And that should be all the input that you need to give. Now, we're all familiar with the rise of AI tools. Everybody's using large language models for text-based prompts and also diffusion models for image generation. You can see here an image that was generated by an AI model. And what did I use for the prompt? Well, I said I wanted a scene with 3 surfers on a wave with some surfers paddling out. And at first glance, this looks like a really good image. It's pretty much met what we wanted it to. But then when you start to look at the details, the surfers in the background don't really have features, but one of the weirdest things is this surfer in the front that doesn't actually have a surfboard, and it doesn't look like the surfboard's under the water. It's just an error. The surfboard is omitted. Now, when we're dealing with photorealistic images, it doesn't matter too much. But when we start to deal with engineering problems where you need a high degree of accuracy, a missing component is a critical flaw. This isn't going to work. Now, with an image generation, it's really not too much of a problem. I don't use too many tokens if I just ask the AI model to try again, generate me 5 more images. And in all likelihood, one of those is going to be acceptable for what I need. And we're seeing a big rise in these tools, LLMs and image generation models. And it's not too difficult to create a new one now. You can see a map of some LLMs plotted on the graph here, and the level that they're getting to. They're getting very good, near to human level reasoning. So this is based on the fact that there is a large amount of training data set available. The internet is a public source of data that these LLMs can use and train on. So it's a perfect training ground for generating a large language model. Also, images are able to use very large public data sets of images, and they're getting much better now at generating things like photorealistic images. Again, there's very large data sets for them to use. But when we start to think about engineering, most organizations keep their intellectual property close. They don't publish it out to the wide internet for large language models to learn from. So it's much more difficult to build engineering-based AI models because there isn't the public data available. So we need to take a bit of a different approach. It's also a lot more difficult to train a foundation model that understands the entire physics of the whole simulation spectrum. So you may be able to train a model that knows how the FEA on a bracket works, but it's a different problem set to train an AI model how the CFD of a turbine works. The two things are very disconnected and very different compared to responding to someone's question in a large language model. So this is the problem that we've approached, where we're looking at the sort of situation where you want to design me a pump that does the following. And I say it's difficult, but the first set of tools are starting to emerge in the industry that can automate parts of this process and put it together. So in terms of reading and understanding and responding to RFP requirements, we have tools coming out in that space. There's also tools for generating system architecture and high-level concepts, and tools for generating mechanical and ECAD automatically as well. Of course, there's simulation tools that are doing the performance evaluation and connecting up multiple physics, and this is where SimScale obviously fits in. And then there's tools for the manufacturing, the shop floor processing, and the ordering. So for the documenting and RFP management, there's various tools that manage that. We have text to CAD, things like Leo popping up, and configuration management tools such as generative or bench that can do generative design processes based on various configurations, low code tools such as Synera, and also then we're going into the simulation part where SimScale fits in. And all of these tool sets are starting to be able to communicate with one another to have a high level goal, such as designing a pump that meets a certain requirement. So in order to do this, there needs to be a high level of automation with CAE in the loop. So if we consider a situation here where we want to prompt to say, design an energy efficient pump that achieves a 10-meter head at a flow rate of 3 meters cubed per hour and runs at 3,000 RPM. What we need there is a tool that can take those requirements, generate a CAD geometry, can simulate the CAD geometry, and can also reason with the results that it gets, and create new CAD geometries to have an optimization. We may also have other use cases like valves, cooling cold plates, solenoid valves. The use cases that you could have for this type of scenario are endless. And the one that we've focused on in the last couple of months to provide an example of how this can be done is a centrifugal pump. And we have two systems that can help with this from an AI perspective. There's physics AI, which allows you to predict the performance of a pump based on a surrogate model that's generated from a large data set of simulations. And we have engineering agentic AI that can be used to help with all of the interconnect of the different tools and the overarching process management for the whole workflow. So it can help you to automate the process and evaluate it all. So the first step that we took to being able to do this was to build a physics AI model for a pump. Now, many companies have done this already. It's quite well understood methodology. So we wanted to take this a step further and build a foundation model for a pump so that essentially you could put in any CAD geometry and predict the performance of that at a specific operating condition. So obviously this sounds great, but you may say that you don't have the time to invest in training a model and validating it. You might be waiting for the right project to come along that will give you the data to train on. There's this chicken and the egg situation with AI training. Is it worth generating that simulation data to train a model when maybe I would just find out the answer that I need while I'm actually creating the training data set? And questions like, how do I know if this will produce sensible results for my application? Well, in SimScale, our solution takes care of all of these things. We have the data generation, the data preparation, the AI model training, the model management, and the deployment of the model. So I'll show you this in the demo, how it all works together very seamlessly. And in order to get past the question of, is it worth creating this data? That's why we decided to create a foundation model that we would then make available to the industry and could serve as a great starting point. So what exactly is a foundation model, and how does that help us in this situation? Well, essentially here, the foundation model is a pre-trained AI model. You can pick it up and you can use it straight away on your designs. You can start getting value out of it immediately. But what really becomes powerful with the foundation model is you can enrich it with your organizational data. So you can take that foundation model and it provides you with a base camp, a starting point, in order to get to the summit of having a fully trained and customized model to your specific designs. It gives you a low barrier to entry starting point. So with this base camp, this foundation pump model, it already knows what blade angles, numbers of different blades, scaling of the pump, draft angle sizes, draft tube sizes, different blade configurations do to the performance of a centrifugal pump. Obviously, it may not know your exact centrifugal pump geometry and topology. That's why you may need to do another 50 to 100 simulations. But then when you feed those in to the foundation model, you end up with a highly customized AI model for pump performance that you can then use. So one example of how this can work for accelerating a CFD example of a centrifugal pump. At the most basic level, SimScale provides an end-to-end CAE tool that enables you to simulate, and you can get huge data sets very quickly and easily using the cloud. Then we have the physics AI capability. So this will allow you to predict the performance using that foundation model. This can be done through the UI, giving you instantaneous results plotted onto a CAD geometry using the pre-trained foundation model, or it can be done through the API. And that's where things get really interesting, because then it can be coupled with some agentic engineering AI. So you can have an AI agent which serves as your main point of contact in the software, and that can then automate many other processes in the background. Post-processing, can also run other tools, either through MCP protocol, talking to another AI agent in another tool stack, or just by writing code on the fly to interface with another. So that could be a CAD tool to actually generate new CAD geometries. And then this opens up the ability to do things like an instantaneous optimization. So if we have a situation where we have a new pump to design, we know roughly the operating regime that it needs to operate in, and we've got some starting point geometries. We could ask the engineering AI agent to go away, run an optimization study using the foundation model, and then you can get data points plotted literally as quickly as you see them coming in on the screen here, because instead of running a simulation in the loop of an optimization, the AI agent can use the foundation model in the loop and get instantaneous predictions of the performance, the efficiency, and the power of a pump. And then you know a really tight parameter space that you want to focus on with a deeper examination using CFD or physical testing to get a better understanding of the performance in that exact location. So the business case here is to respond almost automatically to RFQs. So read the RFQ, understand new product development programs, decrease the simulation lead time, decrease time at task. So for a specific engineer or team of engineers, they can outsource a lot of this work to an AI agent. And then obviously reduce the need to have physical testing and legacy CAE tools. The impact of this on the engineering team is obviously a boost in productivity, increased product performance, and increased cost to performance metrics. So this obviously is a bit of a challenge to implement, and it's only possible with the sort of simulation tool stack that we provide with SimScale. Traditional incumbent CAE tool stacks that grew over time aren't necessarily scalable and able to produce this level of integration. So let's look, for example, at the traditional tool stacks and how most engineering companies started to simulate. So maybe there was a simulation deployment strategy. You implement one tool that covers one physics. That's on a workstation somewhere in the business under the desk. And that's how many organizations started simulating 10 or 20 years ago. Then you add to that separate preprocessor programs, separate solvers to cover alternative physics. At this point, maybe you're getting to the point where that computer under the desk isn't powerful enough to be able to run more than one simulation at a time or large simulations. So maybe at that point, you move to an HPC. That could be on-premise or in the cloud. Maybe then you have some in-house scripts that you've built, expertise that you've developed in-house to be able to run these different solvers, CAD plugins, cloud tools. All of this is a fairly disjointed simulation strategy, which may have excellent power and ability to solve individual problems, but it doesn't scale, and it gives you a simulation lead time in the order of days or weeks. It doesn't allow you to respond rapidly in hours or seconds. With SimScale, we provide a cloud-native CAE stack with GPUs, CPUs, and AI capabilities to cut the simulation lead time down. We take care of the whole of the HPC and IT infrastructure. We provide best-in-class simulation methods and broad physics capabilities to be able to handle these. This is deployed purely through the cloud, and that allows you to achieve the hours or seconds that you need to be able to get to respond to these sorts of questions. So for the actual foundation model, we've generated a pre-trained model here. There's thousands of simulations gone into this, with many geometrical variations, many different types of pumps. Obviously, it doesn't cover the entire spectrum of pumps. We're talking here about centrifugal pumps. It doesn't cover positive displacement pumps, for example. But we've covered a wide breadth of operating points and geometry variations. And this gives you that foundation model that we talked about, that starting point, base camp, to be able to get to your final result. We've done this in partnership with Nvidia. So we use Nvidia's Physics Nemo AI engine in SimScale that's fully integrated. It used to be called Modulus. You might know it by that name. And this enables the instantaneous pump optimization workflow that I talked about. And this really unlocks that RFP response agent type workflow. So if we have a RFP and we have a baseline, as I mentioned before, we can do this automatic design point exploration where we're literally using an AI agent to run the whole optimization workflow for us without having to write a lot of laborious interconnecting code between different tools, and just allows us to get to that final answer that we want, an optimized design for our design point, as fast as possible. So that's the background. I want to spend a bit of time showing you how this really works in the platform now, because I think that's some of the most exciting things that I can show you is some real live demonstrations of how this works. So in the first demonstration, I want to show you how we can take a simple CAD geometry workflow and just generate a simulation out of it in SimScale using the UI. I'll show you how SimScale is hosted. It's completely in the cloud. So all I need to do is go to simscale.com, go to my dashboard, and here I have access to everything. I don't need to launch any local tool or any desktop application. This is all running in the web browser. So I have access to my projects here. As the admin, I can also manage spaces and users, so I can manage who can access AI training, who has permission to do that, and also administer the AI models that are released, and also my projects. So say, for example, I wanted to run a simulation of a pump. It's very straightforward for me to start a new project. So I'll say new pump simulation. So this starts a new simulation project, and I can bring in my CAD geometry from any supported format, which is literally all the proprietary and intermediary file formats. Or I can work from a simulation template. So in this example, I'm going to import a simulation from another area. So I'm going to import a pump simulation from a template that has been put together. So this is how SimScale is helping many organizations. Lots of our larger automotive customers use this sort of workflow where experts in the organization pre-prepare simulation templates that have the required mesh settings, boundary conditions, and so on for the project that they're likely to run. And then the design engineer just needs to come in here, put a new CAD geometry in, and start their simulation. And they can very quickly and easily get high fidelity simulation results. We have many different physics available in SimScale. Obviously, there's CFD capabilities, but there's also structural analysis capabilities, highly nonlinear capabilities with things like MSC hexagon mark implemented now in SimScale, as well as electromagnetics analysis. So a broad range of physics can be accessed directly in the platform. And there, within a few seconds, I've started a simulation. There's absolutely no load on my local machine at this time. I can continue to do other sorts of simulations. So maybe I would want to do a parametric sweep over multiple different flow rates. I can import those from a CSV file or type them directly in here. And this will now start a parametric run of 3 simulations in parallel. So there, in the space of a few seconds, I've got 4 simulations running in the cloud using up to 196 core machines per simulation. And I'll get an email notification when those simulations are ready for me to review. So very easy, straightforward workflow. Now, that's the high level CFD capability. But we're here to talk about AI and how that's going to change things. So the thing that I want to have a look at next is how we can predict the performance of the CFD using an AI model. So I'll show you the foundation pump model. So what we're going to do is open a project that's the same one that I used for that simulation setup, the same template essentially that I used, but in here I've got multiple different pump geometries. I can see multiple different geometries here, very different CADs, very different pumps. Some of the examples that we used when building this model. So you can see they vary quite significantly. And if I go to one of the setups here, I can get an instantaneous prediction of how this pump would perform by launching the foundation model. So this will take a few seconds through the UI, through the API. It's actually a lot faster. And now I can see the performance. I can see the pressure plotted directly onto the geometry. And importantly, for any external workflows that we want to set up, we've got those scalar result predictions as well. So the power, the efficiency, and the pressure increase created by the pump. And obviously, any changes that we make here to the setup will cause an instantaneous change as well. So I can change the flow rate, and I'll get an instantaneous prediction again of the performance based on that flow rate. And this works for any of the boundary conditions, any CAD geometry changes. So I can see the new performance plotted. And if I change to a completely different CAD geometry, I'll also get the performance plotted again on this one with the predictions of the efficiency and the performance of the pump as well. So just as an example, a very different CAD geometry. Again, we can see how that one performs, can interact with the result and see the scalar results. And then let's just change again to another different CAD geometry. You can see this one has a completely different volute and draft tube design, different impeller design. And again, we get the performance plotted immediately. So as a design engineer, you could very quickly get insights from this. We can see this pump has quite low efficiency. There's definitely areas to work on here. And without having to wait for minutes or hours for simulations to complete, we can just iterate very quickly through different designs in order to meet that hours or seconds that we need to get the simulation cycle and simulation lead time down to be able to respond to RFP and RFQs in a much shorter amount of time. So that's the first level of improvement that we can make there. Now, the other thing I was talking about is the completely agentic approach to being able to interface with an AI agent and run much broader tasks in the background. And our vision here is really for simulation to be something that happens in the background, and for the engineer to really not have to worry about how to run a simulation, how to set it up, but more to worry about the insights that they need to get out and the understanding that they need to make from the final design. So we have some early capability available for this right now that I want to show you on another automotive example, say a manifold. We can see an inlet manifold here. And I'm going to be setting up a simulation and understanding how this works purely by talking with an AI agent. So this is a RAG LLM that we've got fully integrated into SimScale. And you've got control to choose the provider that you want to run on. So I'm going to run with OpenAI, and I'm going to give it some high reasoning effort. So then I can ask very broad questions in here, but let's ask what simulation has been run here? Because maybe this is a simulation that was set up by one of my colleagues, and I don't understand exactly what was done. The LLM has complete access to SimScale, to our documentation, and everything that a large language model has access to on the internet as well. So here we can see it's confirming that we've got a linear, static, structural analysis on this model. So, you know, the next thing I could say is something like, what would be the next best step to optimize this? Optimize my structure. So then again, it will consider the input and give us some hints on what we should do next. This might be setting up a different simulation. It might be running this one. And this is all going to be trained and based upon the knowledge that it has of your industry as well. So this is going to be specific to training data that you provide it. It's going to be specific to what you've done in SimScale in the past. So here it says set up a topology optimization study using your current loads and fixed support to trim excess material in low stress regions and minimize weight. So yeah, that's a great suggestion to optimize the design. But how about NVH? Because maybe I want to consider the NVH of this design. And as a design engineer, I might not know exactly what I should do as the next step to do that. So it's fantastic to have a tool like this that can really interact with you as a user and give suggestions. So here it says for NVH, start with a frequency analysis to extract the natural modes, then set up a harmonic analysis to assess stress state and vibration under your excitation. So great. Set up a frequency analysis. So this has complete access to SimScale via the API. So it can do everything that a user could do while interfacing with SimScale. So it can now go into the simulation tree, as you've seen. It's set up a new frequency analysis. And then it's telling us what we would have to do next in order to do this. So it says assign a material, then define mode count under the simulation control. That's currently set as 6 modes, and then set up fixed support. So yeah, go ahead and assign the materials based on the name. So it can do extra reasoning as well. In this circumstance, we've got the material for each of those parts in brackets. So the LLM can understand that. In this circumstance, it's quite an easy data set to access, but that could be buried somewhere else in some settings of the part that was imported. It could be materials data that's available externally in a CSV file or in a database. It can then go and access that data and bring that in and populate the simulation with it. So here you'll see the screen flashing a couple of times because it's actually taking control. It's just assigned aluminium to the components in the assembly here that we've got. We've got a gasket and some bolts in there, some sleeves. We've got some titanium fixture bolts that it's just assigned as well. And then I think the final thing is the casing of the inlet itself with a polymer material assigned to it. So yeah, that's the final step, assigning ABS to the casing. So we're almost ready to set up a simulation. I think the final thing that we would need, as was recommended, is a fixed support. So great. Now add a fixed support where you think it best to do so. So even if maybe you don't know where the right place is to add the support, it can do some reasoning on the design. Our AI agent is trained on all of the data that we have in SimScale. We have 600,000 users of SimScale worldwide. A lot of those are community users, and all of the data that they provide on the community is public data. So we're able to use that to train our models. So it's able to reason from this that this face would be the one that would be fixed for a frequency analysis. So that's done. Go ahead and start the simulation with the 6 modes. So we can go ahead with the default settings there to generate 6 modes, and we can run a frequency analysis. And this is a fairly simple example, but you can see how I haven't had to actually interact with the setup manually at all. This has all been through the AI agent. And I'm obviously doing this in the UI here so that you can see how it works. But this AI agent could be interfacing with a separate external tool via MCP protocol or another way of communicating with a separate agent and running all of this in the background without anyone actually having to give it the prompts. So this is, a demo so that you can see what's happening. But the possibilities to be able to do this are really endless. It can go pretty much anywhere by running in the background and doing all of these things remotely. So obviously we could go on here. I had a couple of things on my notes to go ahead and set up a harmonic analysis. We can go to the level of understanding whether we should be using ERP to understand what parts might be creating resonance and creating noise in the assembly. But looking at the time, I think that's probably a good point to stop there. We've got the simulation basically set up. So yeah, we can tell it to run the frequency analysis. And that's one of the first examples completed. Now, the other area where we're getting a lot of benefit from this sort of tool is accessibility and local language. So SimScale is used in many parts of the world, and in some areas the language can be an issue. If in Japan or Korea, it's very difficult to translate the entirety of SimScale into local language. But through an AI agent, we can say, talk with me in Japanese now. And then it will actually do all of the communication with us in that language that we selected. And we could say, for example, summarize the entire simulation setup. And now it'll give us a full summary in whatever language we want of what's actually been done. So if you work in a multinational team where there's engineers doing things in different languages and you don't understand exactly what has been done, specifically for Europeans, if something's been set up and the CAD geometry uses Japanese characters, or Japanese characters have been used for the boundary conditions, or the other way around, it's really easy to translate that and get an understanding of it. And that can obviously be in any language. Please do that in French now. And then we'll get the whole thing translated in French as well. So this is another example of how it opens up many possibilities to be able to interface through any language with a tool that might not be accessible otherwise. Okay. So the final thing that I want to demonstrate is how we can actually train these physics AI models and deploy them using SimScale. So I'm going to show this part using a video because I don't want to create another version of the foundation AI model. I did this a few weeks ago when we were generating the foundation model. So first of all, you can see the AI training permission that as an admin, you have control over, and you can control who can access models. So the first thing to do if you want to create a new physics AI model is to obviously give it a name and a description in SimScale. And then once you've done this, you can start to set up the AI model. And as I said, we make this incredibly easy. So creating an AI model is as simple as creating it and then choosing the geometries that you want, choosing the simulations. So the foundation model is based on thousands. In this example, I selected about 1,000 simulations. And then when this is submitted for training on our GPU infrastructure, we automatically segregate some of that data as unseen training data so that when the training is run, we're always doing a regression analysis and checking the AI model at every iteration against some of that unseen training data. So there, it's scheduled now. That's going to take a couple of hours to run on a GPU. While that's running, we can do things like adding documentation so the team members know how to use it, and we have it ready for publishing in the organization. So fast forward a few hours, this is where we would get to. We can see the training loss and information from the actual training of it. And this is the foundation pump model. At the time, it was at about 4,000 utilizations. It's at over 10,000 now. So that's it, deployed then within the organization. And anyone that has access to it can pick it up and use it and use that AI model to make predictions. And as you saw, the UI and interface is very easy. If you have more data that you want to make use of, you can just plug that in and retrain the AI model to your needs. So if that caught your eye, how can you get started? Well, we can provide to you trial access to SimScale and access to the foundation model. We have an example SimScale project that this can all run on. We've collected up an example script in a Google Colab notebook that contains an optimization script. It contains a on-shape model that you have access to and the SimScale license. And we can provide access to that for up to 30 days so that you can use our Nvidia Physics Nemo powered AI surrogate model for a pump. And there's the whole data set there. We want to open source this as much as possible so that we can see what people in the community can do with it. And it serves as a great example, as a first starting point, a foundation for generating that tailored inference AI model that you need to use in your organization. Now, when we get to the point of actually training your own data sets, feeding in extra data to that model, that's where we come in with services and with technical support to help you get that final mile and produce an AI model that's truly valuable for your organization. So please reach out to us and get in touch if that's of interest. You can request a one-to-one demo by visiting simscale.com. You can scan the QR code here. You can contact us directly either at sales@simscale.com or using my email, slna@simscale.com. And in most cases, you'll be contacted by one of my team within one business day to understand your needs and help you get value out of AI. Thank you.